Definite. Okay. So today we're gonna study the electronic structure here a little bit more. Probably will continue that on the next lecture. So last time we looked at non-adiabatic dynamics, conical extraction, that sort of stuff, potential energy surfaces, something that is important there. And in the real situations, you need to obtain this potential energy surfaces from somewhere for first principles modeling, right? So that's where the electronic structure problem comes in. To remind you, we have this problem to solve, and the electronic functions that sort of parametrically depend on the nuclear positions. So we fix the nuclei. Electronic Hamiltonian is kinetic energy plus all potential energies when we fix the nuclei. Right, and so this is the part as well, just to make things physical. Otherwise, the surfaces will not account for the nuclear portion. Right? And these parts contain electrons. These are the easy parts. And this is the hard part. Now this is super easy, right? Why this is super easy? Because it has terms like this. And this is the summation over nuclei. And it's just a number. So it's not really an operator for this problem because we fixed the nuclei, right? So these guys are easy because they are one electron operators. And electrons are indistinguishable. We'll talk more about that. So they are easy because we can solve them exactly. This part can be solved exactly. When I say exactly solvable, what I mean is that if we can always construct the function for 1 to n electrons for multi-electron function that will be a solution for this Hamiltonian, just this part. All right, and we know how to build this thing if we know how to solve some one electron Hamiltonian sort of problems. And I'm not saying that these one electron problems are analytically solvable, but since they're one electron, that means the functions here are 3D functions, and we numerically can solve them. Okay, and then once we have those functions for single electrons, we can build from them the multi n electron functions, and that is non-trivial problem for the general problem for this, right? But for this part of this problem, it's easy. I'll show you how to do it. So let's say this is some E0 or rather some E0 phi. So okay, so I guess you all probably have some knowledge of the electronic structure, right? Problem. So is that correct? Like you studied the electronic structure. Right. So here, I guess we'll go then just more like a review, I guess, to make sure that we covered this problem. Okay, so then we have the problem. There's this hard part because it introduces the hard to the left part, right? And then there's the easy part. There is a trivial part, which is number. Okay, and then how do we generally approach the problem? We will try to, as I said here, we'll try to build this solution out of products of the single particle functions. Right? So that's the basic idea. So we have, let's say, some multi-index K, and we'll have a product over phi being I, one, and electron, right? So we should have something like this, where here, I guess, n large n, and should use large n for electrons, something like this. So then, assuming that these functions are coming from some one electron equation, which we will clarify later. So, but you already probably know that there is like Hartree-Fock equations that usually people use for creating these one electron functions. There is also other equations. It really doesn't matter. If we go after the exact solution of this problem, what one electron basis one uses is not important, because if you have a space of one electron functions, then and you take all possible, I guess, combination of let's say if we have n functions and n electrons, if we have all possible products, then we should be getting the sort of the exact answers to this problem with n electrons within of course this basis that is in this case truncated at n orbitals. These guys usually called orbitals, and they are somehow obtained either using Hartree-Fock method that we will talk about, or you could use some other methods. Sometimes people use DFT or Bornstein methods, but that has some issues. Now, the choice of these orbitals make a difference if we don't go after the exact solution, which is called usually full CI, full configuration configuration. Right, so if we go for the full configuration interaction, meaning that we will take all possible combinations of products with all coefficients optimized. How do we optimize coefficients? We could use variational ansatz, right? That's what people usually do. They put this in variational ansatz and sort of minimize with respect to the coefficient. That gives the energy. It's numerically exact. very difficult to obtain, of course, because this is combinatorial. That's why full configuration interaction, full CI, in short, it's only can be done if the system has M within the like maybe dozens of the orbitals, 10, 20. Now, when you get to the 30, it becomes already difficult for supercomputers, and then 40 is, I don't know what's the current record, but essentially people, I believe, were able to do maybe benzene with the relatively large basis sets. So the M is order of 30 probably, something like that. But this is more always considered to be a method that one can do on a computer to get the exact answer for small systems, right? And the purpose of that exercise would be that, by the way, this minimization problem sort of leads to the Hamiltonian coefficient, the eigenvalue problem, right? And that's what is kind of making things hard is that this Hamiltonian matrix, which is the matrix in this product for our electronic Hamiltonian, that matrix is just exponentially large, or this large by another number like this. Okay, and then, yeah, that's what this actually is making this problem hard for the applications. But people usually develop some approximations, numerous ones. And for those, to study those approximations, it's kind of quite natural. Take a small system like a hydrogen and small basis. The basis sets we will talk maybe later about. There are like different names for them. And one of the smallest ones, like STO3G, where say you have 2 electrons, 2 basis functions. And in this small basis, you could do this kind of full CI calculations exactly, see what's the exact answer is within the basis. Right, so it's not the result that you can compare with experiment, because the problem is that the functions that you use to approximate these functions, they are limited. So we are not really using very flexible construction to solve one electron problem. And that's why the number of the M number here, sort of I goes from 1 to M. So this M number is small, and that's why you could sort of, you're not at the convergence yet. So in order to compare with experiment, you need to use the larger basis sets, and then you could compare to the experiments. All right, so you came late. Is there like a setup clear, or should I explain a little bit?
Can you go through it for once?
So we're solving the electronic structure problem, this one. So which is the part of general problem. We skipped that. We went to the non-adiabatic dynamics last time. But in order to obtain potential energy surfaces, we need to solve this. So today I'll talk about how do we solve it, and various aspects of its solution, various methods, and we will cover probably this lecture, and the next one will be about effectively solving this problem. Okay, so this problem boils down to what the Hamiltonian is. Of course, the Hamiltonian has 1 electron part. It's called 1 electron, not because it's just a single electron, but because all electrons are indistinguishable, and these guys effectively have 1 electron operators in it. And this is the easy part. It can be exactly solvable, meaning that if you have 1 electron basis obtained from somewhere, we'll talk about the Hartree-Fock method, say that is one way to obtain this 1 electron functions. Then there is a way to construct a function which solves this problem. And you could also add the V and N part to this problem. It's also super easy because the N part is just a number that corresponds to the nuclei, right? So why is it a number, not a function?
Wait, what?
Why this term is not a function? Seems like it has these variables. I'm claiming this is a number, which does make the problem harder. But clearly it has the dependence of the nuclear positions, the vigors. See, you're not listening actively. It's bad. Because you could miss stuff. So you should question everything that is not clear. But for that, you need to care what I'm saying. If you don't care, sure. But in this case, what is the problem I solving?
You're finding a surface,
What surface?
potential energy surface.
What is that?
That's basically a plot that we discussed last time.
Yeah, so then you can tell it now, right? We discussed it last time. So you can tell us
Well-
now what is the potential energy surface.
But then how does that relate to this being a constant?
Yeah, how? Anyone?
Because we freeze the nuclei.
That's right. So this is analogous quadratic equation where we have ax squared plus bx c plus c, and where a, b, and c are fixed, right? So a, b, and c are r's, big r's, they're fixed. So these potential energy surfaces we talked about last time because we were using we needed these energies, electronic energies, for different r's, right? And so we calculate them at every r, but once we decided, okay, we need the potential energy surface at this particular r, then we just freeze the nuclei at that big R. So this guy is a constant, this guy is a constant, why this guy is a constant? Yeah, anyone?
You know the charge. You know what.
Then charges. What is this law? Where does this come from?
It's basically the potential energy sum of all.
It's the Coulomb interaction between the two charged particles. One has Z alpha and another has Z beta, right? And they are positioned in these positions which we froze, right? And that's why this is a constant, because everything here is a constant. Okay, so then we fix the positions and we are solving for what are our variables, small r's, the electronic variables, right? And so the Hamiltonian has 4 terms, it's a constant. So why is this easy for any eigenvalue problem? If you have an operator function and you know the solution, let's say like this. So what will be solution for the problem where we add constants? Same solution. So we don't need to look for the function again. And the eigenvalues will be just shifted by that constant. So we add this constant to potential energy surface to make it look more physical, because if we don't put it here, for the hydrogen case, H, the electronic energy would be like this. Right, so here we have helium. two hydrogen collapse to each other in the nuclei, right? So we have a helium, and it seems like the hydrogen and hydrogen, they should collapse to each other. If you don't account for this part brings the sort of the Coulomb repulsion, and we don't have collapse. That's why it's convenient to have it as a part of potential energy surface, because that's what the force that the nuclei sort of feel, right? So the whole idea of Born and Oppenheimer separation of electrons and nuclei is that we want to solve the electronic problem and think about and sort of don't think too much about the electrons anymore. Electrons, the effect of the nuclei would be that they provide potential energy on which the nuclei are moving, right? So we're done with electrons once we solve this problem. Well, multiple roots, of course, because the states can intersect, stuff like that. Or if they intersect, then we need to account for the couplings in the nuclear motion. And that becomes more difficult. We looked at that last time. Okay, now today we just dwell into how do we solve this problem. And okay, so I said that can solve the multi-electron problem by combining products of one electron solutions, right? Multiple versions. And this is simply the result, like why one single product cannot do the work. And that is another question one can ask. Why, if we solve for, let's say we have helium or hydrogen, or let's say hydrogen is more molecular, right? So we have a hydrogen, has two electrons, right? So why can't we solve just for one hydrogen, another hydrogen, right? So we know in quantum mechanics we can solve for two hydrogens. This is one electron problem, this is one electron problem. We have functions for each electron are one, and here the same functions pretty much. Let's say JR2, right? And so why can't we just make a product and say, all right, we're done?
They have a bond, so the electrons are delocalized. I don't want to.
Yeah, this is all chemical words that everyone likes to say, but what do they really mean? You're not a chemist anymore. We're not chemists anymore. We have an eigenvalue problem to solve. Why this is not a solution? Explain to me. Bond. Where do I see bond here? There's no bond. There's no delocalization. There are operators. Right. So why this is not the solution for the electronic structure problem?
Because they aren't separable.
Again,
Where do we see that in the problem?
because this one ignores the attraction from the other nucleus and the repulsion from the other electrons of the other atom.
Okay, so which of those things can we add?
In VE, a part of VE, the electron nucleus attraction from the other
Right,
nucleus and
That's
the
correct.
repulsion from the.
that's correct. If we find this guy as just a hydrogenic atom solutions, then it ignores the essentially PEN is sum over Z alpha. Q electron in atomic units is like 1. So, but we have Ri, R alpha, right? And so here we have sum over I and alpha, and this should be negative, right? Because of attraction. Sure, but potentially now we could get this problem, get the solution of this problem, phi's from taking the electron nuclear for a particular I, right? So say for first electron, which would be just the sum over alpha, the alpha minus R1 minus R alpha, right? So we can do this, right? Plus we could add the T electron 1, plus we could add B and N, right? So we could combine all that, for the first electron, and for the second electron, will be exactly the same. And so that way we can obtain these guys, because it's like a one electron problem, obtain them. It will not be any more hydrogen molecule problem or hydrogen atom problem, it will be effectively H2 plus problem. So that's what we can solve numerically. Actually, H2 plus is it's a exactly solvable, the only exactly solvable molecule case of one electron, two nuclei can be done. And but it's still missing the electron, right? So that's why this single product is not going to be a solution. Because there's a coupling between the electrons, right? So now the eigenvalue problem basis, eigenvalue problem sort of by language, you have like two operators for two electrons, plus you have coupling, and that coupling electron coupling that makes necessary to mix the products. So now, how do we mix the products? When it comes to the mixing the product, there are lots of coefficients generally, and there are lots of products we can put, right? But what helps usually to avoid growth is symmetry, right? So that's the very important point here. How do we build the products accounting for the symmetries? So what sort of symmetries one would expect in molecules? I'll list them all, but let's start thinking about that. Okay, so what symmetries do you know for molecules?
Spatial.
Spatial.
Yeah.
Rotational.
Rotational, is it the same as spatial or different?
Same.
Same, okay, so spatial symmetry. One, spatial symmetry. Symmetry, what it means is that there are operators that are acting on the effectively coordinate system that changes the coordinates of electron, and effectively because we have the nuclear frame that has a symmetry, bringing the electron 1 from here to electron 2 sort of here, exchanging them spatially, it's not gonna change things. So we have symmetry operations based on the framework of the nuclei, right? Okay, what else? The spatial symmetries or point group symmetries, they are important for highly symmetric systems like hydrogen. It has this infinite order axis, right? So mean that no matter what angle here we use to rotate, it's all the same, right? So this system should be symmetric or antisymmetric, or essentially it should be somehow when we rotate, the wave function should have certain properties with respect to this rotation. That's how symmetry helps, right? But also we have sort of a plane here, right? That we can do an inversion with respect to the origin. Great. So, but there are systems which are like proteins. They have almost no spatial symmetries. Okay. So that's why this is not the first and the most important part of the electronic structure problem, because sometimes we don't have spatial symmetries. For some molecules we do, for some we don't. What else do we have?
Is electron indistinguishability.
Electron indistinguishability, right? So fermionic nature, indistinguishability. electrons, right? So what is that? Exactly. How can we,
You can swap the position of electrons to still get the same energy.
if we have two swap where? So yeah, so they we have two objects, right? So electron Hamiltonian, which depends on R1, R2. Right, and let's say for hydrogen case, some R's. So if we switch them, Hamiltonian doesn't change, right? So because then Coulomb electron interaction. Here they enter the same way. Here they are just R1 minus R2 essentially like this. So the Hamiltonian doesn't change, right? So that's why it's symmetry.
But the solution has to be, the wave function has to be negative when
Why?
ions change. That's just the definition of fermion.
Right, that's just the definition of fermionic functions. That when you exchange any two coordinates, then you have a sign. If you exchange two pairs, then you of course don't get the sign minus, you get sign plus. Now, how is that related to indistinguishability? It seems like we, oops, made a mistake. 2 R1. So it seems like we label them, we change the order, we get the minus. How is that indistinguishability?
Well, the wave function has no physical, not a physical entity, but the density remains the same. Even the design changes.
Okay, so effectively we have distinguishability that coming from this relation, probability density, right? Because there are multiple densities in the electronic structure theory,
Okay.
1 electron, 2 electron, n electron density. So we're talking about n electron for this case because we would like all the electrons to be present, and this object or its square doesn't matter really. So that this object is containing the coordinates of electrons in the same way, right? So because this is something that we can observe, in this observable quantity, we cannot, based on the labeling, we can essentially distinguish what is the first electron, what is the second. The way they enter the way this observable depends on them is the same, right? But this allows us to have minus or plus here, or actually in general any phase. But turns out that most particles are either fermions, bosons, and fermions have minus, bosons have plus, right? Okay, great. So this is the distinguishability of electrons. And what does this construction require us to do? Effectively, these products that we have, right? They should be ideally following this symmetry. We could, what will happen if we ignore sort of, we can say, all right, these coefficients must take care of that, right? Attention. Right, because these products, to have this condition, you may say, all right, well, let's say one particular way of constructing it, if we have phi1 R1, phi2 R2, minus phi1 R2, phi2 R1, right? So one way to build a function like this would be taking two products and doing the minus sign in front, right? So then when you exchange, you get that minus or overall minus. And if you look at this and you look at the general expression, so you can say that this minus could come from just the coefficient right here. And everything will be fine. Is that the case? Can we simply continue with the product and ignore that indistinguishability in principle? Of course, as I was talking before, all the symmetries, they help to reduce the number of coefficients that you need to really obtain. And here, if you know this, then in some products, you will have positive, some negative, so there will be few coefficients to obtain if you account for this somehow. So then, let's say in the case of just the two electrons, half of the products will go with a positive sign and half of the products with negative sign. So then it simply means you reduce the number of coefficients. Great. But can you just ignore that and go and optimize this problem, or minimize with respect to coefficients, without putting that constraint that coefficients should have a certain sign with respect to each other? Yes or no?
No, I think this constraint needs to be manually put in.
Why? What's gonna happen if you don't?
Because the Hamiltonian doesn't have any information of that it's a fermion or equilibrium. Nothing written has that.
Okay,
That's why I think it should be manually put in.
okay. But what's gonna happen if we don't?
Then I'll just minimize without taking care of it. That's
What if this solution is minimal?
I think it's still we have a minimum solution, but we will have a family of minimum solutions.
What's that? Degeneracy?
Yes, generous.
Okay. So then it doesn't matter. We will obtain one of those.
Yeah.
Oh, actually, it does matter, because if you don't do that, you will violate the kind of Pauli equivalent principle, right? So for lithium, which we know that the main configuration is something like this, right? For lithium, you will have bosonic solution, as they say, or 1s3. Because indeed, Hamiltonian doesn't have any information about spin, doesn't have any information about the exclusion principle. It just doesn't care. So it has the symmetry where you exchange R1, R2, and it's the same Hamiltonian. That means the function could be symmetric or antisymmetric with respect to exchange of the particles, coordinates, right? And this is one solution. Another solution would be the plus, right? So fine. And it turned out that the plus solution sometimes is lower actually. So, and you will collapse to the wrong solution. So it is crucial to account for the distinguishability of electrons and that the electrons are fermions. And what is the construction that allows us to do it? Remember? Slater determinant, right? Slater determinants allow us to do that. That's why we should, if we want to solve this problem, substitute the product by Slater determinants. Right. Now, what are the Slater determinants? This is a kind of interesting construction that allows you to have this property. Essentially, I already wrote it here. Right? So this is in a form that just the sum of products, one with some products with coefficient plus, some products with coefficient -1. But more formally, this one just comes from the phi 1, 1, phi 2, 1, then phi 1, 2, phi 2, 2. So divided by, usually for normalization purposes, by n factorial, in this case 2, right? And so this thing will be exactly this, we just have square root of 2, okay? And in general, if we have a particular set of orbitals, K1 is the starting orbital, and they go up to 5 K n and electron here 5 A1 so K1 and 5 A n. This was all this one. That's fine. Okay. So remember, you kind of change either this index along the row, then you keep the electron coordinate the same, right? Along that row, and then you change the electron coordinate along the column. Okay, so I hope everyone is familiar with determinants, and we will be using them to construct the wave function. General. Now, how it turns out that in order to write matrix elements or determinants, it's convenient to know another alternative way of writing them, and this is something comes from linear algebra. So this is a sum. When we expand the determinant, like in this case, it's the sum of n factorial terms. So we have these permutations. So what permutations I'm talking about here? There is such object as a group of permutations. What this means is you have numbers from 1 to n. Permutations would be 1, 2, and so on. Will be all sorts of let's say constructions where they essentially say explain where should you put 1. You could permute 1 with any number in between 2 and n, right? So in this case, the 1 goes to 2, 2 goes to 1, and then the others stay the same, right? And then you could do, turns out, these things form a group. What this means is that there is a way to kind of define the multiplication, which is quite straightforward. If you have one permutation like this and another permutation sigma 2, let's say is 1, 2, 3, it's always the top same sequence. But then here we have, let's say, 3 and 1 exchange. Right? So then the product of these two you apply to this sequence, the sigma 2, the 1 goes to 3, and sort of 3 goes to 1. Now, after that, you apply sigma 1, and in order to apply sigma 1, you look where the 3 goes to 3, and then 2 goes to 1, and 1 goes to 2, right? So that means that this is a permutation where if you start with 1, 2, 3, and so on, you go to 3, 1, 2, right, instead of 4 and 2 n, right? So you clearly can just apply them one after another. And there is a permutation that is sort of identity where 1, 2, 3, and so on goes to 1, 2, 3 without any exchange. So that multiplied by anything will give you the same thing that you multiply this for. Also, there is always the inverse, sigma 1, say -1, would be the permutation which goes 1, it goes 1 to 2 and 2 to 1. That's the same thing. So this is self-inverse. So if you do it twice, you go back to the same thing. Right? So this is all the long way to say that they form a group. The groups will be, if we will have time to study a little bit more, because there are some formulas that we will see today, and we saw already. They're kind of nicely coming from the representation of the group theory. Like if some operations they form a group, then there are certain things are easy to develop. And so what today we will see is that this determinant actually is a sum over group elements. What I mean by that is that you have this factorial sum where you have a sign in front of each product, and the sign in front of each product is related to the parity of the permutation, which I haven't defined yet. What parity is, turns out that the entire group Sn, it's called, of all these permutations, any element, sigma I, can be written as a product of so-called cycles, meaning that you have K exchange with L, right? And then KL products like that. So essentially, any permutation can be written as a product of permuting just two indices, right? You can always do that. And whether the number of such permutations is even or odd, effectively parity is that. It's either number, well, parity could be seen as a number of cycles. And it turns out that there's no way you could change the parity from even to odd. It's always going to be even number of cycles for a particular permutation of odd number of cycles.
Then isn't this the same as the Levi-Civita symbol?
No, it's different.
Is it? That's
But they are related because
just a parity.
if there is a parity there
So
in the exchange.
You couldn't use that here.
Levi-Civita is for, I guess, particular tensors. That was
Yeah.
my impression, which I guess we can write with Levi-Civita symbols, some say SU2 algebra expression for the commutators of the spin. But yeah, you could. This is more general because it's n, and it's permutation parity for the actually group of permutations. You could. I haven't worked much with the Levi-Civita, and I know that it's related to the tensors, and there in tensors there is also sometimes questions about this antisymmetric symmetric. So, but you should look it up. Maybe there is a deeper connection. I don't know. Okay, but this is the number of cycles in every permutation, and that's why this number becomes either +1 or -1. Those are the only two, 1, 1. And then what follows here is the product of our orbitals, and the product is, we could either write it as sigma k I That's one way to write it. So we essentially permute the indices of the orbitals, or you can write the same thing as the as a fitting tutorial and one sigma. But here in the product, we can write phi k I. We keep the indices just going in the order, whichever they ordered, and then here we have our coordinates permuted. Okay, these are both the same because you could either start decomposing determinant in the kind of minors based on the row or the column, or if you transpose the determinant, it's the same. It's the same construction. So then you will get a different order. So either way is fine, but that's what is essential is that all these products, they are organized with the coefficients that are like this. Now, turns out that this is nothing but just older brother of what we already see. Like if you have a function F and you have a group of parity sort of operation, that what it does, it takes P of X and goes like this, right? We talked about this symmetry. P square is identity, so they form a group, P and identity. And then for any function, there are two types of eigenfunctions of this parity operator, symmetric and antisymmetric. And then if you want to symmetrize your function, what you do is you do 1/2 f of x plus f of minus x. So what this really is could be put in this form. Well, it's already kind of in this form, but more specifically, it's the number of group elements to identity parity, and then here we have nothing happening to f of x, and here we have parity happening to f of x. Right? And so coefficients are 1/2, and here is as well 1/2. If you want antisymmetric version, then you put minus here, right? So the coefficient changed for this term. Now what's going on here? We can also write what's going on here by applying some operator to the products, okay, of functions, and in this case, the group is bigger. The group is Sn, so it has n factorial elements, not just 2 elements. Here it's an identity element and the parity element, right? So only 2 elements. But the same idea, and it turns out this is a very general idea. That's why studying the group theory is useful, because whenever you have a group, you can always symmetrize and essentially symmetrize. That's what generally people call this operation, because even though you can get symmetric and antisymmetric, they have a clear symmetric property that now either symmetric or antisymmetric function is an eigenfunction of this of group elements. Okay. Now there's a little bit of a caveat here that sometimes operations that form the group, they don't commute. In this case, for example, Sn, if you go beyond n equals 2, go n to n equals 3, then there is no commutativity. It's meaning that if you go sigma 1, sigma 2, it could be different than sigma 2, sigma 1. Okay? So in this case, again, there's everything commutes, so that's why we can find eigenfunction for all the operations in the group, and these are these two eigenfunctions, symmetric and antisymmetric. But in the bigger groups, sometimes we cannot find common eigenfunctions for all group elements. And this formula then constructs so-called the next best thing. What is the next best thing? If you have no operators that don't commute, you construct a function that form irreducible representations, meaning that they form certain blocks where if you apply all the group elements, so the function, let's say that you symmetrize like this, it will go into other functions inside the same block, right? So the case where things commute correspond just to the diagonal situation, right? So where if, let's say you symmetrize function here, and you apply 1 to the function, that's the function itself, so eigenvalue is 1. If you apply parity, depending on the S of A, you will get minus or plus 1 when P acts, but the function doesn't change. So this function is sort of eigenfunction for all the elements of the group because the group has only commuting elements. But if group contains non-commuting elements, then the only thing you can build is the blocks, so that some element of the group will take the function and will move it to a different function. So it's formally not an eigenfunction anymore, but that function which you obtain will come back to this function, say, if some other element will act on it, or yeah, essentially something like that will happen. And so you could construct these block structures. And the block structures are good because then you have what kills the efficiency of quantum mechanics is that the matrices of operators are big, right? And if you have symmetries, the matrices could be reduced to the block diagonal structure, and then you need to diagonalize if you're interested in energy, say, only within a certain block, not the bigger matrices, right? So that's the whole idea of symmetry. And over back here, it's the same formula where we go over the group elements, apply them to the product that we want to symmetrize or anti-symmetrize. In this case, it's anti-symmetrization. And multiply by some coefficients to understand why these coefficients come in this way, or 1/2 plus or minus here, which looks similar. But generally, these coefficients are more complex for different groups. And that requires, how do we get these coefficients? That requires, for arbitrary group, that requires studying group theory. It's not that complicated after all, the form of the coefficient, but where or why do they form, why do they look like that? That requires some group theory consideration, okay, which we'll hopefully do closer to that. All right, so now one more. Like I just want to write this in this form, in the form of some operator acting on the product, and that will put us in the position where we can, where are we going with this? We're going with this to ways we can formulate matrix elements of our Hamiltonian with symmetrized products, a linear combination of symmetrized products, right? Because that's what is needed for variational solution of the electronic structure problem. Right? So we have this Hamiltonian. You already remember, have this problem, and now what we will have is the construction of phi written as a linear combination, but over determinants. Okay, and these determinants, they are 1 over n factorial, the square root phi k1, 1 phi k n 1 k1 n phi k n, right? But we want to write them a little bit differently. Okay. Write them as we can write them as 1 over n factorial, but with 1/2 positives, right? Apply and we will define this operator that is anti-symmetrizator. Applied to just a simple product of I goes from 1 to n phi k I, okay. So this is a simple product corresponding to, you could think of it as like this diagonal, right, element. This matrix, because k1 for 1, k2 for 2, k3 for and so on. This part. It's a simple product, right? And then we antisymmetrize it. What is the antisymmetrization operator? Antisymmetrization operator is the following thing. It's the n factorial, but now with -1. And this change of normalizations is needed just to make this effectively a projector. That's what I want. So this guy to be projector, which will help with the manipulations. So to derive some very simple, nice expressions. Got this -1. The rest is pretty much the same as before. Here we have a sigma as an operator. Right, so we sum over sigma operators that are from the permutation group. We account for the sign. And when we apply this to the product, then we either, it's up to us, we either change the ki or we change the arguments according to that permutation, right? So this is an operator, and it turns out it is a projector. So if you apply it twice, which is natural if you start antisymmetrizing the determinant, then you get back the same thing, determinant. So there's no point of antisymmetrizing it. It's already antisymmetrized. That's why it's sort of a projector. Okay, and that property of the being a projector, Hermitian as well, it will help us to some relations, otherwise complicated. Okay, so this is what we know now, and I can safely erase all that. And where we're going with this is a few things that, by the way, we mentioned 2 symmetries out of 3. So there is a third one that we didn't mention. It's a spin symmetry. I will talk about it later. All right, so, but I guess the 2 most important symmetries in general in the electronic structure are the spin and, well, indistinguishability and spin, because then the point group symmetry, it depends on whether your structure, nuclear configuration essentially is has some symmetry, or it's maybe non-symmetric, and you cannot use much then point group symmetries. All right. So now the idea here is that we would like to minimize, based on the C's, the phi problem. Right, so that's the idea, and that's the simplest approach. Phi is like this, right? And naturally, once we have the Slater determinants, we will need to consider matrix elements of Slater determinants. By the way, in general, we already know that this problem results in the matrix C equals to, well, generally it's overlap, but we'll see that the overlap could be substituted by identity. Okay, now what are these guys? Just to be sort of from first principles, the Hamiltonian would be one Slater determinant, because that's our basis. Electronic Hamiltonian, another Slater determinant. Okay, so we need these matrix elements, easily obtainable, and it turns out there's a name result, there is a so-called Condon rules. Condon rules. There are rules, Condon rules, they can be derived. It's not that. Yeah, you can show them. There is also, interestingly, I don't know whether that's the same Condon or not. I will check by next lecture. In spectroscopy, there is a Condon approximation, non-Condon approximation, and we'll talk about that too. And Frank Condon factors. So it seems like it's the same Condon, but I need to check to make sure that's right. Here it's called Condon rules, or sometimes Slater Condon rules. And to give you a gist of it, it turns out that let's say if you have some D0 starting determinant on the left, then H D K is not equal to 0 only if the K is different from 0 vector by less or equal than equal to 2 indices. 2 indices. So effectively, this K is like K1, Kn, and this one is 0, 1, 0, n. So what these guys are is like indices of the orbitals, right? In the basis. And what this is saying is that these numbers and these numbers, assuming, of course, here orthogonality of all these orbitals by j, that different orbitals are orthogonal. So assuming orthogonality, the only non-zero matrix elements are coming from 2 determinants that have differences in the set of orbitals not more than the 2. The only 2 orbitals could be different, meaning that, let's say if we have phi 1 to phi 10 in one, let's say this was our determinant for D0, then the only determinants can be coupled through the Hamiltonian to this determinant. They are, let's say 1 is substituted by 11 and 2 is substituted by 12. But if this is like our decay, right? But if we have 3 substituted by 13, then the coupling element is 0. Okay. And Y2, again, going a little bit ahead, is just because the electronic Hamiltonian has either 1 electron or 2 electron operators and no 3 electron operators, meaning that VEE is the 2 electron operator. It couples the 2 coordinates. Others cannot be different. Others, if their other orbitals are different than 2, then there will be, because of their orthogonality, 0 essentially. Okay, so this is like a big picture of what Condon rules are. I will clarify what the expressions are and how we derive them. That's kind of the idea. But the problem here is that we want these matrix elements, and they are useful for many approximate methods of solving, because this is only one particular way of solving. Another way is, and the simplest way would be, we can ask the following question. If we have in this sum a single determinant, just one determinant, how do we optimize orbitals so that the energy, this energy, is the lowest? Okay, so that's the Hartree-Fock. Okay, and with a single determinant. this is called, with more than one determinant is called configuration interaction. Configuration interaction. And if you do all possible determinants, then it's a full configuration interaction. That's the exact answer in the particular one particle basis. Okay, but to derive Hartree-Fock equations and to derive what the matrix elements are, Slater-Condon rules essentially, we need to consider this matrix outputs, because for determining Hartree-Fock method, we need just the one matrix element between some determinant and determinant gain with the component. Diagonal element where k is the same as 0. Right? And then this matrix elements turns out to be also useful if you want to do, say, perturbation theory on top of the Hartree-Fock. Right? So Euler-Plessen theory uses that as well. So they are cornerstone of the electronic structure based on the Condon rules. That's why they're super important. And they all can be derived relatively easily using this anti-symmetrization projector. Okay. All right. Now, what do we have? Okay, so the simplest Condon rule, I guess, would be, and quite useful in other places. We will, I guess, yeah, it's easy to start to see how this works. And the starting point of this rule is that if we have two determinants, it's like rule number 0, rule 0. If we have two determinants, d0, say, and dk, right? And the determinant and the orbitals in the d0 and the dk, they are not orthogonal necessarily, right? So just the general orbitals. So that means we don't have this. Generally, we just have in this determinant we have phi I orbitals, and in this determinant we have phi ki orbitals, right? And they are not like phi I overlap with phi k j is not equal to delta ij or something. It could be anything, right? Then one can ask the question. What is the overlap between d0 and dk? And that's it. We'll see the general formula, and from that general formula, we can see what will happen if we make sure that these guys are orthogonal, right? So now it turns out that here it's an overlap between the two determinants, and nicely, it is determinant of the overlap matrix. And the determinant of the overlap matrix is like essentially, let's say, so this matrix is phi I, then phi aj. Right? So we give you kind of an impression. Let's say we are working with I running from 1 to 2, right? Simplicity. So then this guy is phi 1, 1 electron. So it's phi 2, 1 electron. Phi 1 with 2 electron. Phi 2, 2. So that's the determinant. this guy is, let's say, phi. Well, to make it simpler, let's say it's some other. Not to use double index, but just a single index. Phi 3, 1, phi 4, 1, phi 3, 2, phi 4, 2. Right? The question is, what is this is an integral over two variables, 1 and 2, right? And it turns out it's the same as determinant of phi 1, phi 3, phi 1, phi 4, phi 2, phi 3, phi 2, phi 4. Okay. Very kind of simple and nice formula. Again, if these things are not orthogonal, if they are orthogonal, then clearly you get 0, right? Between if f3 and f4 are different than 2 and 1, and they are all orthogonal, then all these overlaps will be just 0, right? Even if 3 equals to 2 and only 4 is different, then still it's enough to have one guy that is orthogonal to others, then you have a whole column with this guy to be 0 essentially. And if the column of the determinant is 0, then of the matrix, then the determinant will be 0, right? So this is a very nice formula, and then it is it could be of use when you, let's say, in molecular electronic structure theory, when we go on the potential energy surface and calculate matrix elements between functions at the different r's, r0, r1, right? So here we obtain orbitals, here we obtain orbitals, and those orbitals, the set of orbitals here is of course orthogonal. One orbital is orthogonal to all other orbitals, and here they're mutually orthogonal, but between the sets they are not necessarily orthogonal, right? And so then if you want overlap between the determinants, then you get the sort of these formulas, and even in this equation, to the like for the full electron function, if you calculate phi I at R with phi J at R, two solutions. That's the same R, they are orthogonal. But if there's a different R, they are not necessarily orthogonal. Okay, so for this, they are not Ij. If R is different. Okay, so how do we essentially derive this formula? We write down, we're using definition, we will write down this expression using the anti-symmetrization projectors. And then we will see that effectively we'll use the fact that there will be two P's, that one comes from this guy, another comes from this guy, even though this guy is with a Hermitian conjugation, but because it's Hermitian conjugate, it's a Hermitian, then we could use this formula, and then it will boil down to just a single anti-symmetrization. And single anti-symmetrization will lead us to the determinant. Okay, so that's kind of the idea here. Just I'll illustrate. So what do we have? Let's see. We have. Formula, okay, each determinant is given as n factorial. And then what we have is inside. Yes. On the E phi zero i's. Here. Product of my AI. That's what we have. Then we move this guy, it's an operator here. Right, so using the fact that PAS permission same as PAS. Right, and the fact that the square of PAS is less than PAS, what we obtain is n factorial, then product of phi 0 I, and then yes. And this ends up being formula for determinant because, well, this PAS contains 1 over n factorial, which cancels this 1 over n factorial. Okay. So that means we just have the sum over factorial number of elements, sigma n minus 1 by parity of sigma. And here we have overlap of the I, and let's say I prime, because this I that I kind of unrelated technically. Here we have sigma I prime, right? And this is the determinant that we want, because if you think about it, the inner product here only maps the I with the I here, right? So this kind of, if we have, yeah, we integrate the corresponding variables. So that means we have product over i's, phi over I, I, each I, phi, sigma, A, I. And this is pretty much determinant of the overlap, because we have significator here. So we have all possible products of the I index with Ki, and Ki is just a shuffling essentially between n. So this is the simplest zero quantum rule one can derive. Similarly, we can go ahead and sort of write down the rules corresponding to one electron, two electron operators, so on. Yes, first I can write what the rules are. So if we have five determinant 0, H determinant 0. This is something that we will need for Hart-Fock equations. Then this becomes, let's say, for shortness, I will write that for the H, there will be two parts. The one electron part, just define as like A operators, I, 1 to n. So these are effectively, in our case, is electron nuclear plus kinetic energy, right? Because they all have this one. Single electron coordinate and sum over all coordinates. Right. Plus, we have two electron operator, I not equal to j, half b by j. Right, that's our DEE. Because it contains pairs. Okay, so then with this definition, turns out this rule becomes sum over this I, okay, I is an orbital from 1 to n. That is present in the D0, like the 0 case is just yes. Okay, so 0 contains 1 to n set. And we enumerate it with i's. So that is I, A, I. Plus two electron part half. Here we have integrals, two kinds. This and like this. Okay. That's pretty much the rule for the same determinant on both sides. Okay, so we will have this one electron integrals, and one electron integrals is like dr1 is all of them indistinguishable. We can say it's always dr1. Then we have I r1 star A operator or that acts on the R1, I R1. A simple Dirac notation, essentially, for the integral. This one is also formally the Dirac notation. It has dr1, 2, right? And then I R1 star A R2, because this is the like a first, this is the second electron, right? So it goes IJ, then IJ stars, then B R1 2, which is the 1/R12 in our case. And I again with R1 without conjugation, G with R2. So this guy, these two are exchanged. Right? So physically, this usually is called Coulomb integrals, and this one is exchange. And the reason for that, well, we have an exchange of coordinates for particles, but Coulomb is more corresponding to the physical sort of classical physical interaction of the probability density for the I orbital with the probability density of the J orbital, right, through Coulomb interaction. Oh, here it's a product of Ij with Ij. Okay, and then in quantum chemistry there is also a different notation, which is called, this one is called Dirac's notation. Dirac's. And it's usually with angular brackets. There is also Mulliken notation. Where people use what they do, they group R1 first and then R2, right? So that means this integral would be, there is a round brackets usually. This integral would be II J, and this one would be Ij, right? So Ij. So this is a little bit confusing sometimes, but usually if you read in the literature of quantum chemists, they like to use this one. This is more like from physics people, but physics people don't do molecular electronic structure. So it's a less common. So this is a small common, but this is just for you to be aware of so that you won't get confused. Okay. Good. All right. So this is what we're gonna use for the, say, Hartree-Fock method, because in order to derive Hartree-Fock, now we have everything. We have energy of a single Slater determinant with some orbitals, i's and j's, right? So the same set, like some set of orbitals, and what we the point of Hartree-Fock is now to minimize this energy with respect to variation of orbitals, right? And we already studied variational approach in its full glory, meaning that you can vary functions using variances statistics. So variations of function, right? So in the undergraduate courses, usually if the Hartree-Fock is discussed, then people right away write this as a linear combination of atomic orbitals and change the coefficients, right? So that is, the coefficients are numbers, so you kind of do multivariable calculus essentially. But to derive true Hartree-Fock equations, one should write the differential equations on these functions. Okay, so we need to work in an infinite dimensional space because each of these functions is a 3D function where at every point it can have any value it wants, right? So that's what the variational calculus gives us. If we do it right, so then we should get the differential equation that is equivalent to minimizing this thing, minimizing with respect to orbitals phi I. So we minimize phi i's that enter the zero sort of determinants or Slater determinants. Okay. So that's the idea of Hartree-Fock. All right, now few other Slater rules. that are also very important. I will, okay, I'll erase this space. And write down two more Slater rules, because two more Slater rules will correspond to these elements where this determinant we substitute one orbital or two orbitals, right? So that those are the two other cases. And if we substitute more than two orbitals, then it's always zero. Okay, so that sometimes is also called, I guess this is the consequence that there is zero, the consequence of distinguishability of the particles, and in the language of maybe quantum information, is that the Hamiltonian is too local, meaning that it couples only two particles at a time, not more. Because if the Hamiltonian, imagine the Hamiltonian would have, it needs to be symmetric with respect to exchange. So be it, like let's imagine you have C function in it, which has Ri, Rj, Rk dependence, right? And we had like a sum over various exchanges of ijk's, so that it's symmetric. Ijk. If we had the Hamiltonian like that, then we could exchange three potentially orbitals in the determinant and still have non-zero elements. But we don't have that yet. In some theories of electronic structure, the electronic Hamiltonian is modified to account for inter-electronic interaction. And then that exchanges, sorry, not exchanges, but that those modifications, they lead to more particles being coupled at the same time. So those are called trans-correlated methods. If we have time, we'll talk about that. But for now, this is kind of goes a little bit beyond. All right, so now let's see if we substitute. In zero, we're substituting N1 by L1. Right, so some orbital N1 substituted by N1, L1. Those are the differences. So essentially this one has all up to the n, and this one, one and one out of this range is substituted by L1, which is outside of this this range of orbitals. Right, so for the case of let's say n equals 2, this one has phi 1, phi 2, and this one will have phi 1, phi 3, right? So that's the kind of example. In this example, 2 is n1 and 3 is L1. And this guy is I. Okay, so the formula then looks like this. It's just for the one electron part, it's N1 a L1. So clearly this guy comes from the D0 where N1 is present. This from this guy where L1 is present instead. And you have sum over I and 1 B L1 I minus N1 I B I L1. So formula And this goes from 1 to n. Now, the last one will be formula where we have D0, H, D, that N1 and N2, substitute by L1, L2. That's the last one. And there clearly only electron guys survive. 1, 2. And 1, 2. So that's it. Now, what do these formulas allow us to say actually about essentially this matrix is that the usual construction of this say configuration interaction picture, selecting which determinants, like if you want to go beyond the single determinant, you want to figure out which ones to put. And the usual way what people do, they first determine what's the best set of orbitals using Hartree-Fock method, right? What's the best set of orbitals? What's the best single determinant? And you can sort of express, we'll see it in a moment, or when we will finish the Hartree-Fock. So probably next lecture, that this set of orbitals, they will have sort of associated one particle energies, right? So these one particle energies could be used to arrange the orbitals in that based on those energies, right? And then some that have lower one particle energies, they will be occupied. So these are type of diagrams in chemistry people like. Right, so this could be the determinant, meaning that it contains 2 phi-1s with spin alpha and beta, 2 phi-2s with the spin alpha and beta, and well, for the lowest solution, and if you are interested in a single determinant, probably you'll put this. If you have 5 electrons, you'll put the fifth one on the third orbital, right? And so that is your D0. Let's say in the example of 5 electrons, when you obtain these 5 orbitals by minimizing this energy, right? So when Hartree-Fock energy where the D0 is here and here, that's what was there in the beginning, right? So once you obtain this, then you could construct other states, other determinants, by promoting some of these electrons to the higher orbitals, right? And you could look at all single excitations, all double excitations, and of course, the more excitations you consider, the more configurations you will have, right? And what this actually tells us, these rules, is that the matrix of the Hamiltonian in the basis of these determinants, it will look like something like this. So this one is the 0, 0. Then there will be all single, like this is 0, this is singles, these are all doubles. And here the same singles, doubles, and so on. Right? So these are the kind of blocks. Then the matrix goes by triple excitation. Triple excitations. Now, from this, we will see that potentially 0 only coupled up to doubles, right? So this block is already zeros, right? Because if we substitute 3 orbitals y something, then it will be 0, right? And according to, so it's bad notation. So here, let's say we have a Hartree-Fock energy of the Hartree-Fock. So it's not 0, but here we have something. Here we have something. We will also show that for case of Hartree-Fock, these guys are 0 too. But this doesn't follow from the rules of Slater. Oh, sorry, Slater-Condon, right? It's just follows from the Hartree-Fock theory. But what follows from the Condon rule is that essentially singlets or single excitations, they are not connected with more than triple excitations, right? So that whole matrix is all relatively sparse. Okay, because there are lots of zeros, since whatever determinant you have, if you excite more than twice, then that's it. It's already decoupled. Okay. So yet this matrix, of course, is exponential in size, and can be solved only for small problems, right? So I want to start the Hartree-Fock, but we'll start the next lecture with discussion of Hartree-Fock and how it works, what sort of versions, what are the problems. Okay.